Great. So this is with a function for a function with an oblique slant asymptote. It's a lot, so I'm not going to write it out as I speak. Instead, I decided to put all of my thoughts down and kind of just highlight and walk through it. Um, I'm going to use this purple highlighter right here. So, basically, we're going to start off with this function right here, y equals 3x to the second power plus 4 divided by x minus 2. So, mainly the things that you want to look for when you're graphing functions, period, would be the x-intercept, the y-intercept, and the asymptote. And that helps you position where the function is in the graph so that afterwards, if you're stuck, you can plug in x and y values to get your points and plot them. So first I started off with the x-intercept. So in order to do that, you would have to set the function equal to 0. That will help you find the x-intercept. And in this case, I went through um, the whole cycle, all of this down right here, and I ended up with an imaginary number, x equals plus or minus imaginary number, square root of 4 over 3, and that would give us an imaginary number, obviously, which means that there is no x-intercept. Um, and that will play into finding the asymptote later and finding out what the asymptote is. So for the y-intercept, you plug 0 into x. So did that right here. This is my process, and this is the answer that I came out with, -2. So I just write that right here. Um, Asymptotes. So for asymptotes, so this quadratic does not factor because there was no real solution for the x-intercept. So take the denominator and set it to 0. There's nothing you can do with this function. As it said, this did not, because it cannot factor, and so there is nothing to cancel out, which would also mean that there's less possibility of there being holes in this function as well. So that's exactly what I did. I set the denominator equal to 0, and it gave me +2 for horizontal. So typically, um, typically the numerator should equal the degree of the denominator, or um, less than, but the degree of this numerator is larger than, like, one larger than the denominator. So there is an oblique asymptote. So in order to find what that is, you would have to do polynomial long division, and that is basically the process that I went through here. And I came out with this remainder, which is 16. Essentially, I rewrote the function as so, with what I had come out with, and essentially this would be equal to this, vice versa. And 3x plus 6, which is what we got right here in the top portion of our polynomial long division, would be the oblique asymptote. So basically all you would have to do from now is to graph it. So basically I started out with putting down my y-intercept and my little, what do you call it? My y-intercept and my x, um and there was no x, but I also ended up put I let me slow down. um so I ended up putting where the denominator, when I took and when I equaled set it equal to 0, this is where I graphed it, and this is my oblique asymptote right here. So from then on, I decided that I was going to take x and y, and start. So I chose points of -3, -1, 1, 2, and 3, and basically substituted all of these numbers into the function. Here's an example of this, but I didn't want to include it because I thought it would be too cluttered. And essentially, I started graphing them. So we have the points right here. Some of the numbers, like 31 and 26, were too far to graph, so I just roughly drew it up here. But essentially, this is the graph that I ended up coming up with. So it's a lot of extensive knowledge that you would have to know to graph these, but it's not as terrible as it may seem.